Okay, I think that's gone. Yeah, so I got sick on Friday, so I spent my weekend in bed. But I'm back. My voice is not completely back yet, so apologies for that. Let's motivate what we're doing. So we're doing inverses. So I figure let's do something that we're all familiar with, because if you attach what you're familiar with, the analog concept is going to be much easier to handle. So if I took 5 and I multiplied it by this very specific element, 5 to the minus 1, what does that return me to? 1. If I took the element negative 6 and I multiplied it by its corresponding special element, minus 6 to the minus 1, what does that return me to? Okay. In general, with real numbers, if I select a real number x, what do I need to multiply my real number by to return it to 1?
X to the middle.
Yeah, x to the minus 1.
Potentially stupid question, PSR. If there was no parentheses, then that would be 6 to the negative 1 with a negative in front of it. So there would be a negative of the result, correct?
Yes.
Okay.
So, this the behavior, 1 is a special element with multiplication, because 1 is the element that says that 1 times anything will always return back the element. In other words, this element for multiplication functions as an identity. When I have an element, the fact that I'm guaranteed the existence of some other element in this set that allows me to return to the identity, we consider this the concept of inverse. Does that make sense? An inverse is an element that corresponds to some other element in my set that returns me to whatever the identity is for the operation. Okay? So what we're going to do is we've talked about matrices. And so we're going to expand that discussion and say, if I can think of a matrix as taking a vector and transforming it into something else, then is it possible for me to start with the output vector and figure out how to undo that transformation to get back? Essentially, can I find a matrix for another matrix that functions as an inverse? So let's make a definition. An n by n matrix A is said to be invertible. Invertible. If and only if there exists, so again, what does this symbol mean, everybody? There exists an n by n matrix C such that CA is equal to AC, which is equal to IN. Okay, so in other words, some matrix that doesn't matter if I multiply it on the left or the right, of my matrix A, that's going to return to the identity. So think about this. This is kind of like my A, and this is like my C, returning me to the identity 1. And these are now just matrices, CA or AC to IN. Further, in this case, C is an inverse. So we can call the actual matrix C an inverse of the matrix A. And this is very important, unique. So since it's unique, we can give it a special notation. So we'll denote A with the typical inverse notation like we're all familiar with. So, as a matter of notation, instead of thinking about it as CA and AC, I could think about this simply as if I took the inverse of a matrix A and then multiply it by the matrix itself, this should return me to the identity matrix. And another way I could get back to the identity matrix is if I did A and A inverse. So the order both of them have to work. Okay. Some more terminology. That's all related. A matrix that is not invertible, that is not invertible, is called, or not always, but can be, that's more appropriate, can be called a singular matrix. So this is what we're defining, singular matrix. And an invertible matrix can be called a non-singular matrix. Before I forget to mention it, whoever's sitting in that corner, Chloe, would you mind tearing out a sheet of paper to do the completion for the readings and attendance as well? Thank you. Okay, so how do I remember that singular is not invertible? Well, because if you are invertible, that's implying the existence of essentially its counterpart, its buddy, its inverse. So with Valentine's Day coming around the corner, for the most of us, we do not have our inverse, and we are all singular, okay? So I am a singular matrix. Everyone is, most of us are singular matrices. Actually, it was funny, in Greek grammar, we have something called a masculine singular, and that's how we bully all the Greek 4 students who stick around that far. So, at any rate, okay, questions about terminology. So does this make sense? So the matrix A is invertible if it has an inverse, but we don't call the inverse like the invertible. We call this just simply the inverse. And if there is an inverse, then the original matrix is what we then say is invertible. Or if you want to use singular or non-singular, that terminology also exists. Okay. So here's a quick theorem. I'll give you an overlay of what this lecture is going to look like. First thing is I'm going to show you the direct computation method for the 2x2. Okay. Finding inverses of a 2x2 matrix, it's just a formula. It's a very easy formula, and you can compute those anytime without much complication. And then from there, we build up to the language to then generalize finding inverses just in general. Okay. So first, given A, so again, for the 2x2 case, so let's just call this A, B, C, D. The inverse of the 2x2 is always going to look like this. It's a formula. 1 over AD minus BC times, and then what we're going to do to the actual matrix is we're going to have A and D swap places. B and C are going to stay where they're put, but then we just negate them. So A and D swap places. So the D is down here and the A is down here. B and C are going to stay in the same spot, but they get negated, so minus B minus C. So that's one way you can memorize the formula. And with all things in the formula, you should be able to plug and chug pretty straightforward. But there's an actual important definitional thing that's kind of a foreshadowing to later in the course, so I'll include it here. The quantity AD minus BC, so this denominator right here, for the above matrix is called the determinant. Determinant of A. And there's going to be a whole chapter on determinants later, but for now, this is kind of a foreshadowing. So if this is the determinant, then we could think about what happens when this is 0. So if the determinant of my matrix A, which is AD minus BC, what happens if this is 0? And think about just the formula.
The inverse is 0?
Well, if I plug, is it even possible to take 1 over 0?
No.
That's an undefined thing. You can break it. What does this tell us? Well, not every single matrix is guaranteed to have an inverse. You can have matrices that are not invertible. So, if I can find out that the determinant is 0, that automatically tells me that there does not exist an inverse.
For singular.
Now what's nice about this is a great way to visualize, to kind of see the concept with respect to a formula. What we'll find later on in the course is that this still holds determinant being 0, telling you that there's no inverse. That actually stays irrespective of the size of your matrix later on. Now it takes more hardware to actually discuss, but it's nice that it's linked to something easy. So for memory's sake, so long as you can kind of anchor yourself here, that's an easy one to remember for invertible matrices. Determinant 0, that means you're not going to have an inverse. On the other flip side, if your determinant is non-zero, well, good job. We're gonna have an inverse.
Scott,
Yes.
I'm sure we're going to work an example of this, but the way the mechanics of that equation would actually work is that you would solve the constant, the 1 over AB minus BC, and then multiply that by each one of the elements in the matrix, correct?
Mm-hmm. All it says, think of this A, B, C, D representing just like some sort of a real number. That's all that is. These are just constant values. So like if this was 0, 2, 5, and 7, then you would just quite literally plug and chug those exact numbers into the formula, and that will spit out the correct answer. So, do we need to see an example of this with actual numbers?
Or I was just verifying the example.
I wouldn't need an example, but how would that work if he was, for example, like 4 by 4? Okay.
This is, okay, yeah, so that's a good question. This is specifically only for the 2 by 2 case. So this is the case for finding an inverse of a 2 by 2 matrix. We'll talk about like larger sizes, like 4 by 4, 5 by 5, etc., in the next part of this lecture. So we'll build up toward that. For now, there's an easy one. It's just kind of given to us in a formula.
Another question. So having a determinant equal to 0, like you wrote in there, is that the only reason why a matrix would be singular? Or that's not
Good
even?
Those were all different.
I believe so, actually, yeah, because if I'm thinking of later on, we're going to triangulate matrices, and there's going to be a theorem where you can take the diagonal entries of that, and then the product of those diagonal entries is going to spit out your determinant, meaning that if you don't have all of the necessary pivots to get you down, you'll be stuck with one of those that are all zeros across, meaning that you're going to be forced to have a diagonal entry that's 0, and so then 0 times anything is 0, meaning that this should always hold.
Okay.
So yes, that will generalize to all sizes.
Okay.
Good question. Anything else?
Why is the order for the second matrix the way it is?
It's formula. We'll talk about the derivation of this as an example later, hopefully if we have time when we cover determinants in its fuller chapter.
Okay.
But for now, trust me, bro, is the answer. Okay, good questions, good questions. Anything else on this? Okay, we ready to scale this up to general?
Yep.
See, the reason I have to prepare my lectures is because Samika is always going to ask something really, really technical. You got to think about it for a second. It's good though. I like it. Okay. So let's now build toward what I'm going to do. Oh, actually, so this theorem that I'm going to write down is how I was able to answer Samuel's question. So this could actually be really useful. I am now thinking about the fact that I literally just cited this in my brain a second ago. Okay, if A is an invertible matrix, I'll put its size here, so it's m by n, then do we remember what the upside down capital A is in English? Yeah, for all vectors B in Rn, It's kind of easy when you have a square matrix because then you don't have to guess, it's just going to be n. There is going to exist a unique, so that's what the exclamation point is, unique vector x that can be found as taking the inverse of a times b, such that ax is equal to b. What is all this jargon saying? Okay, what this is saying is, suppose you started with this matrix equation. Then if I am guaranteed that there is an inverse, essentially A is invertible, that means there's going to exist its own inverse. So I can take the inverse of both sides. And if I'm able to take the inverse of both sides, I mean, this is very, very analogous to solving like a linear equation like x plus 1. Actually, I'll use multiplication since that's what I did to start. So it'd be saying like 5x is equal to maybe 4, right? So then what I'm doing is I'm citing the existence of the inverse. 5 inverse 5x. 5 inverse 4. So analogously, this is what's happening. And so then, by definition, the inverse of the matrix here is return you to identity. Identity times x. Analogously, identity in multiplication is 1. So it's 1 times x now. It's equal to 4/5. And identity times anything, well, the function of the identity matrix is that it's the one matrix that doesn't do anything. So it's just static. So x is going to be described by this vector. In the same sense, then, 1, it's identity. So it's not supposed to change x. It's the one element that does it. So we're left with x equals 4/5. You've been doing algebra your entire time. It's just that you haven't articulated why you did each one of those steps. You just kind of did it because it's one of those things that you don't need to know what's going on under the hood to do it correctly. But now we're starting to peek under the hood. So that's what this theorem is simply saying. It's that if you have a matrix equation where the matrix itself is invertible, all that's saying is you can undo what you just did. If I want to transform a vector and it's invertible, great. Just undo that action and come back, and then you'll spit back your vector, okay? The key here is it's unique. So that helped me answer, yes, question?
So are you saying that, okay, so if you have the inverse of the A, does that mean that you could inverse the inverse to make it back to A, or do you need to like reverse it completely on the steps to get?
Yeah, that's right. So like if I had an inverse of a matrix, and then I got back to the identity, and then I took the inverse again, all of those work together. It's the same thing as like if I kept multiplying and dividing by 5.
I meant like 5 to the negative 1 raised to the negative 1. Will it be back to 5?
I feel like you can answer that. What is this equal, guys?
Oh, it is 5. Never mind.
So analogously,
Hey.
there we go. So we'll actually, that property we'll cover in a theorem a little bit later, but yes, intuition gets us there pretty quick. Okay, any other questions? Yes.
Are only square matrices invertible?
Yes, we're only talking about the square ones. Mhm.
Can you inverse non-square ones?
No.
Okay.
Because there's a theorem that we're going to build toward that in order to be invertible, your matrix needs to be row equivalent to the corresponding identity matrix. And if you don't have, obviously, if it's not square, then it's definitionally never going to become anything that's identity. Good stuff. Okay.
Can
here's-
I make
here's-
a
oh, yes.
question, comment? Yeah, if you don't have a non-square matrix too, you're actually kind of changing the space you're in. So it's not like if it's like going from 3 space to 2 space or some other. So you can't really undo those things because once you collapse a dimension, let's say you have a matrix that's non-square, it goes from 3 space to 2 space. Once you collapse it to 2, there's no way to recover what you lost.
This is what she's getting at. If you start with vectors in Rn and then spit out vectors in Rm, then yeah, there's no way to get there. You've changed the number of entries that's going to be in your vector. So then you can't undo that. Okay. There is a key takeaway to be had with this little theorem, and that's going to be a key motivation for why we care so much about whether we can invert a matrix or not, is because invertible matrices guarantee the existence of solutions. And of course, in a class where we've been asking the fundamental question of whether or not something is consistent or not all the time, suddenly that becomes kind of important. So if you have something that's invertible, you've now guaranteed that if you use that invertible matrix in some sort of a system, you will have, you'll guarantee the existence of solutions for your solution set. Now whether those are unique or not, we'll determine that in a little bit as we keep going. So a few things. These are just kind of rules for the algebra. Let A and B be n by n invertible matrices. And to claim that these are invertible is to claim the existence of matrices A inverse and B inverse. Then we'll have three little things. A inverse is invertible itself. I mean, that should make sense, right? So if I start with a matrix A that has an inverse, let's call that inverse A inverse. Well then, does A inverse have an inverse? Well, I would sure hope it's just back to A, right? So that's all that's saying. And we can articulate that with just one line of math. Is that I can take the inverse of an inverse. It returns me the original matrix. Now, this is going to look really familiar to something that we covered last lecture. Which rule is this looking like? Which operation did we talk at the very end of last lecture? Transpose. So the way that we do this is now in the reverse order. You do not just distribute your inverse in order. It's always going to be in the reverse. So if it's AB and I'm taking its inverse, I'm going to do B inverse on the left and A inverse on the right. So they switch. And then this one's kind of fun. Is that if I have the transpose of a matrix that's invertible and take its inverse, it's actually the same thing as if I would have started with the inverse of the matrix and taken its transpose. So transpose and inverse have a fun little relationship there. Okay, so if we feel good about this, the rest of the lecture is going to be all the build up to generalizing and finding, like actually computing the inverses for higher dimensions. Okay, are we happy with on the left side?
Yes.
Okay. The way we're going to get to the algorithm for always being able to find whether or not, well, you won't always be able to find an inverse, but you'll be able to determine whether it is existent or not, is we need to define something called an elementary matrix. An elementary matrix is one that is obtained by performing a single elementary row operation. Something that should be near and dear to your hearts by now. On an identity matrix. On an identity matrix. Okay, so what does that mean? Here's some examples. The following three matrices I'm going to write on this board are all examples of an elementary matrix by definition. Let's call this first one E1. 1, 0, minus 4, 0, 1, 0, 0, 0, 1. I'll write all three of them out and then I'll talk about what makes them definitionally elementary. 0, 1, 0, 1, 0, 0, 0, 0, 1. And then 1, 0, 0, 0, 1, 0, 0, 0, 5. Okay, do we remember what our 3 row operations were? Yeah, so we can swap 2 rows out, right? We can interchange 2 rows, and then we can also just scale a row. Okay, so think about, for reference, the identity matrix in 3 by 3 is just 1, 1, 1 down the diagonal and everything down to 0. And so let's take a look at this first one. How can I possibly obtain this specific matrix with only 1 operation away from the identity? Well, I could. So the way I can get this -4 is I could multiply row 1 by -4. And then I could add it to the bottom row and return that to row 3. And if I did that, I would take, for the identity matrix, I'd be taking 1 times -4 is -4, plus, this would be a 0 in the identity, so that's getting me -4. 0 and 0. 0 times -4 is 0, plus 1, so that still returns 1. And so through just this one interchange, I can go from the identity matrix and spit out E1. Does that make sense? This one's a little bit easier to visualize because it's a more obvious what happened. How specifically did I mess up or change the identity matrix?
First and second row.
Yeah, these somehow got flipped around, right? If these 2 rows swap spots, we would actually be back at having 1, 1, 1 down the diagonal and everything else is 0. So the row operation that we used here was we took row 1 and made it swap places with row 2. And so we swapped rows. But at the end of the day, that's only one change. One change that I could easily just undo and get back to the identity, yeah? Okay, what about this last one? What type of row operation happened here? Yeah, we scaled. Which row did we scale? So we scaled the bottom row, R3, by 5, and then we returned that to R3 from the identity. So we scaled. But that's only one operation away. And so notice that for all of these, they are all exactly one step away from just undoing whatever operation we did to return us to the identity. But here, to undo it, essentially the inverse, is just to do the opposite of scaling by 5. Divide by 5. Yes, question?
In example 1, how did you cancel the -y?
That's a 4.
Oh,
Yeah, sorry, my handwriting isn't the greatest. This is a -4, yeah. Does that resolve the question?
Yeah.
Sorry. Okay, for this one. If I wanted to return this to the inverse, undoing this, the inverse, is going to effectively be just swapping those 2 rows back, okay? So this is going to be really interesting. What we're able to see, essentially, is that if we start with an identity matrix, performing a row operation is essentially, we're storing the instructions for how to manipulate to see if a row equivalent to an identity or not, okay? So, well, I'll let me do some computations on this side and the point will make a lot more sense. Say I now have just a general 3x3 matrix A that we don't really know what its values are. So let's call this just A, B, C, D, E, F, G, H, I. Okay? And now what I'm going to do is I'm going to multiply an elementary matrix, one of these, by my A. And we'll see what the net effect is on A, and then compare what's happening. So E1 times A is going to be 1, 0, minus 4, 0, 1, 0, 0, 0, 1, times my A, B, C, D, E, F, G, H, I. Okay? So as I make this multiplication, so for this entry, this is row 1, column 1, row 1, column 1, A, and then 0, 0. And as I go down, right, so now this is the second row, first column still, 0, the only thing that survives is the D. Here, I get minus 4A plus G, okay? So minus 4A plus G, whatever that is. Okay, second column, so we're gonna have something similar. So I'm gonna have B, the only thing that survives. For the second row, second column, E is the only thing that survives. And then third row, second column, I have minus 4B plus H. And then the third column is going to resemble this exact same pattern. C is the only thing that survives. F is the only thing that's going to survive. And then minus C plus I. Or sorry, minus 4C plus I. Interesting. So this product of taking E1 times A is exactly the same thing as if I had started with A and chosen to perform, that was a terrible tilt. What if I had chosen to perform this interchange? Minus 4R1 plus R3 to R3. So we've done this computation separate, but now I want us to do this row interchange separate as well. What happens? What's the output here? Well, the top row is the same. A, B, C, D, E, F is unaffected. The only thing that's affected is R3, right? So I take minus 4 times A and add G, so I get minus 4A plus G, minus 4B plus H, and minus 4C with I. Notice anything really remarkably, coincidentally convenient? Exactly the same thing. Okay, what does this tell me? This tells me that these elementary matrices are essentially storing the instructions in the form of a simple matrix to perform row operations. And if I can essentially, theoretically, hypothetically, store all of those instructions from the starting point of any matrix A and get it reduced all the way down to an identity, get it row equivalent to an identity, its footprint, basically its entire footprint of instructions and ways it's going to affect the elementary row operations is going to end up leaving us only with an invertible it's an inverse, essentially. The inverse being the exact undoing, the list of how to properly undo the row operations on A to get to the identity. So in other words, if I started with A and row reduce it down to its identity, we can keep track effectively and store all of the reverse instructions to get from the identity back to A. And that process of returning back to A is our inverse process. So if that inverse does exist, all we really have to boil this down to is setting up the necessary augmented matrix that can keep track of the row operations we've done so that by the time we finish reducing the matrix we started with to identity, it should leave us with the matrix that perfectly encapsulates exactly how to undo everything else and get us back. Okay, do you want to see E2 multiplied with A and E3 multiplied with A, or are you convinced?
I'm convinced.
Okay, 4 people are convinced of 30, so I'm going to do E2. E2 times A. E2 is 0, 1, 0, 1, 0, 0, 0, 0, 1, like this. Here's A. A, B, C, D, E, F, G, H, I. Okay? So if we do this the computational way, let's see what happens. Well, I have D survives, and then here, only the A survives. Here, only the G survives. Second column, only the E survives. Only the B survives. And then only the H survives. Here, only the F survives. Here, only the C survives. And here, only the I survives. Okay, so now let's start with A. A, B, C, D, E, F, G, H, I. And let's perform a elementary row operation corresponding to E2. In other words, what did we do? We flipped R1 and R2. So let's do that. Let's take R1 and R2 and make them flip. So this becomes row equivalent to what? What's the first row? What's the second? And the third row? So isn't this a lovely coincidence that it spits exactly the same thing out? Okay? So what do we take away? Elementary matrices give us a way to find out that we can actually store the instructions to get back to your original matrix, no matter what that original matrix is to start with. Did it matter that this was a 3x3? Did somehow the constraints of there only being 3 dimensions make this entire thing work, or is it just a general property of the identity? It's generals. Sure sounds like a great place to start for an algorithm to generalize any size inverse. Okay? So here's that algorithm.
Question.
Yes.
What if you have a row entirely zeros, or just a column entirely zeros?
Is it possible to take that and make it row equivalent to the identity?
Yes. Is that possible?
It's not possible.
Doesn't seem like
It's not. And what we'll find is if you have a row full of zeros, it's not going to be row equivalent to identity. And by failing to be row equivalent to the identity matrix, you're failing to have an inverse. Okay? But you might be thinking, hold on a second. I thought that inverses guaranteed the existence of solutions. Why is it suddenly seeming like it's now doing the opposite? Well, with a row of zeros, we are guaranteeing a free variable. Free variables is not just telling me that I have an infinite number of solutions versus just having the identity matrix. This is now a singular, unique solution. So there's the difference between having an infinite number versus just one unique solution. Okay. Alrighty. What time is it? Nice. Okay. So let's find. Well, actually, I should write down the algorithm so that you know what the algorithm is. So, algorithm for finding your inverse. So, we don't care really how big this is so long as it's a square matrix. Row reduce the augmented matrix Now this is going to look a little different than what you're used to for what we mean by an augmented matrix, but it'll be your matrix A, and then these dots are optional, but I like to keep them in there to make straight. Generate the corresponding identity matrix all the way on the other side. So it's not just a single column anymore, it's like a whole like double panel, like if you have 2 screens open on your laptop kind of thing. What's going to happen, here I'll just write it down. So if A is row equivalent to I. So if I can take this down to the identity, then I could basically say AI is row equivalent to, what you're left with is, once you reduce this down to I, what's left is the instructions for how to get back to A. That's a fancy way of just saying A inverse. Otherwise, A does not have an inverse. A does not have an inverse. Okay, what does this mean? That means if I take my matrix A, what's happening over here is this is the matrix that I'm trying to undo. And this identity starter is going to keep track and keep basically all of the footprints of how to undo this. So every single time I make a row operation, that row operation, which we know can be undone on identity, is being kept track of. And then if it's possible for me to get this down to the identity over here, then we've essentially said whatever is remaining on this side encodes the instructions to undo your matrix. If you cannot get to an identity, you found out that your original matrix cannot be undone, so it has no inverse. Okay, does that make sense? So does the concept of it in theory make sense why we've built up the way that we built up to it? Okay, because the actual mechanics of it goes all the way back to the skill that you learned in section 1.1. Good old row reduction. Minutes. Okay, great. Example. Find the inverse of, oh, I'm too short to have started up there. 0, 1, 4, 1, 0 minus 3, and 2, 3, 8. If it exists. Because again, we found out that the inverse of a matrix does not have to necessarily exist. So, what do I mean? How to take this, which is theory, and make it into the actual algorithm? I'm going to say, well, I need to start with A and augment it with an identity matrix to keep track of what I've done to it, essentially, so that I'm essentially keeping track of all the things I need to undo in order. So this is, in this case, 0, 1, 4, 1, 0 minus 3, 2, 3, and 8. So I'm augmenting this with the corresponding identity. So what should this column be?
1, 0,
1, 0, 0.
And then
0, 1, 0.
And
0, 0, 1.
bingo. My matrix A, my corresponding identity that's going to keep track of how things go. Okay, so the first thing that we'll want to do, here's the goal. Make this the identity matrix using any combination of row operations. I'm going to use row operations that I pre-made in my notes because that's how lectures work. But when you're solving your own problems, there's not like a specific order that you have to do these in. Okay, so long as you do legal and valid row operations that get you to identity, you're fine. So what we'll do is we'll do the easy one first. I really want that one to be there, and I really want this one to be there. So let's just swap row 1 and row 2. So row 1 and row 2, we can swap spots. So then I'm left on the top with 103, 012, 4 minus 3, 8. And then over here, if I swapped those top two, then I have 0, 1, 0, 1, 0, 0, 0, 0, 1. Okay. This is essentially E2 from the example before. Okay. What else can I do? Well, we want identity. I have a 1 here. That's already zeroed out. Let's get rid of this 4. I can do that by just taking 4 times R1 and subtracting R3 from it, and then replace R3. So 4 minus 4 will give me 0 as desired. So the top row is unaffected. 1, 0, 3, 0, 1, 0, 0, 1, 2. This is also an unaffected row. And then now the actual affected row. 4 minus 4 is 0. 0 minus a negative 3 is positive 3. 3 times 4 is 12, and 12 take away the 8 is 4. 0 and 0 is a 0. 4 times that 1 is 4. Subtract 0 from it, you get 4. And then 0, 4 times 0 is still 0, negative 1. So now, this is what we've got so far. To continue on making this look like the identity matrix, I have a 1 here already, so let's turn this 3 into a 0. I can do that by taking 3 times R2, turn this into a 3, so I can subtract 3 minus R3, turn that to R3. So again, my top 2 rows are unaffected. 1, 0, 3, 0, 1, 0, 0, 1, 2, 1, 0, 0. And now, 0 and 0. 3 times 3 minus, 3 times 1 is 3, and subtract 3 is 0. 2 times 3 is 6, and 6 take away 4 is 2. 0 and 0. This hold on. We're in the second row, so this 3 times this 1 minus 0 is 3. 0 times 3 is 0, and then I'm subtracting 4. 3 times 0 is 0, and I'm subtracting a negative 1, so this gets signed with positive. Okay? Now this is close, I can scale this by 2, and then I'll have my diagonal of 1s, and we'll be almost there. So I take R3, and I scale it in half, so that this goes to 1, and I return that to R3. So the only row that's being affected is the third one again. So I have 1, 0, 3, 0, 1, 0, 0, 1, 2, 1, 0, 0, 0, 0. Now I've divided this by 2, so now that's 1. 3 divided by 2 is 3 halves. Minus 4 divided by 2 is minus 2. 1 divided by 2 is 1 half. Okay, so I can knock out these remaining and turn those into 0 in one fell swoop because I'm now on the reverse end. So R1 minus 3 times R3 replaces R1. So essentially 3 minus 1 times 3, that's strategic. And then for the second, I have R2, which has a value of 2 there. And I'll subtract 2 times R3 to replace R2. If I do that, then I end up with 1, 0, 0, minus 9 halves, 7 minus 3 halves, 0, 1, 0, minus 2, 4 minus 1, 0, 0, 1, 3 halves, minus 2, 1 half. Is this the identity matrix now? Okay, so we were able to find that the original A is, in fact, row equivalent to the identity. And what we've been doing over here is been storing all of the instructions of how to undo what we've done to get to the identity. That is, this is the inverse. And if you wanted to, you could test it and take your A inverse and multiply it by A. And what will that return you? The identity. And you could do that in either order. You could do it where you do A times A inverse and it should return you to your identity. Okay? So this is the algorithm. This is kind of the main part of the section. If you can do this algorithm, then you can compute or determine the non-existence of inverses for any size square matrix. So if you had a 10 by 10, which you definitely don't have to do on your Pearson because not even I would submit that if I was a student. I'm just being real. You'd be in the I4 lab doing like the entire code of Hammurabi. And so, but the idea is you could do it. You could check. You could get a 10 by 10 identity matrix with 10 by 10 words of instructions how to undo every single thing you did to get back to identity. Okay? Does this algorithm make sense? The motivation and how to actually do it. Yes? Okay. What time is it? Is that going to be my new thing I say every single lecture? What time is it? You guys get out early. Okay. So can I have the paper?
I got it.
That's been going around. Thank you. Yeah, we've got a few more sections left in Chapter 2 before the first exam, so we'll discuss exam review details as we get closer to it. All right, you guys get out early.
What is the exam?